So it's the last token before lunch, so I will try to keep my time at least on time, if not shorter. Well, I thank the organizer giving this chance to talk about the more conventional sort of, more arguably the best candidate for dark matter search and solve the problems. Well, the previous scenario seems to sort of become sort of newly interesting. Then I think many of us believe maybe the cold dark matter has more chance to be detected and verified in some different ways. So the last few questions asked the previous speaker. So I will be concentrated on cold dark matter. But then of course I cannot talk about it all. It's a class of dark matter which is Higgs model type of dark matter. Now my emphasis is the previous, recent new result from Panda X and the Lux, their result, and what new information or constraint on the type of models I'm going to talk about. And then if you want to have more, what do you usually do? Okay, so these two results actually was shown the same day in September in London's dark matter conference. So the two previous each of them wanted their result, knowing the other guys due to report a result. But I think Lux first presented the results of this Panda X guys. See, this group has a lot of heavyweight people, very formally dressed. So they worried about it. So they are going to make a big announcement. Maybe they discovered it, but they only had a sort of upper bound. It turns out the result to be about the same time. They claim about 4 times better than the previous Lux result. Here, in fact, this curve is very similar to this curve. They were more conservative, say, well, 2 times better than the previous Lux result. And but it looks these groups are better prepared. So after the conference, they immediately find you can find on the web page the paper. This come out about a month later. And this paper has published in the PRL. This paper, I think, is still in the reference behind now fighting with each other. But then they have updated the results, combining the previous one and the new one, and get a slightly even better construct. I'll show you later. Okay, so this shows how competing in this area displayed a lot of different thought about what might be the dark matter. So experimentally, I'm really trying to say how dark matter sort of thing. Of course, when you talk about dark matter, you have in the universe, you need to have a model to talk about, and under this model, what are the sort of bucket for dark matter? So you have, if you have the standard sort of Big Bang theory, cosmology constant, and that type of thing, then you will find about 5% U and B and some alike, and then the dark matter is about 27%, and then you this dark energy about 68%. But then, so you want to explain and 27%. So a lot of research has been done. You have seen this diagram many times. So if these are the dark matter, then how they are going to form the relic density, the right number to produce 27%. Of the energy molecule in the universe. So some standard model particle, then the collide and produce the Higgs, all the dark matter collide with each other and produce the standard model particle. So in the early universe, then at some stage, this get out of thermal equilibrium, and then this fixed at some time. And so you, of course, in order to produce 27% of the energy molecule, then whatever this interaction has constraint, and then you know maybe what is the interaction and sort of strength. And then also, if you really at a collider then you just drag 2 protons, and you can produce dark matter, may be able to find some int. But then unfortunately, LHC has not found anything. And then of course you can do this detection and sort of send dark matter hit some target, and go this way and scatter out, and then you measure the recoil energy, whatever form, photon or electron, and temperature rise, heat. And then again, sorry, I don't say it. But then you have the strong bound. Maybe you can constrain whatever model you want to propose, and then you want to tell people, my model solved the problem. And then of course there are also a lot of dark matter, maybe in the halo, that can meet each other and annihilate some standard model. Then you can have this sort of indirect detections. Okay, so this scenario of dark matter compared with the previous Feynman and fuzzy dark matter, you may have more chance experimentally verify it at this state. What else is dark matter? But then in the standard model, you don't have such a candidate which do the job. And of course, then they have seen this plot previously. And then a lot of models are proposed to be just for dark matter. Then you have many different models. Of course, and then if you think about it, from the particle physics history, it's always from simple to a little more complicated, So you ask, what is the simplest, the really simplest dark matter candidate? Then it's just a standard model plus a real singlet, right? This is the real singlet is the dark matter, and then you can do many things. And then you say, well, if this model can explain existing data. So I will not go into all these complicated ones. I will go this one to demonstrate how sort of total dark matter is working and console the dark matter relic density, and then avoid the very stringent bound for direct search. Okay. Well, so of course, then I will be concentrating on the Higgs prototype experiment. So in that case, you need to know how do we know about the Higgs. So the standard model like Higgs, and then it's about 125 dB. Then you have all these separate ratios, and the experiment so far seems to satisfy. Consistent with standard model predictions. So you want to introduce something which not alter the standard model of Higgs maybe too much, otherwise you'll be out of business. So the simplest, as I said, you just introduce a segment. Well, this model, yesterday, Joseph has in the parallel session talked about many of the concepts. So I will go quickly and then see what. If you want to get something more, we need to do. Okay, so this D is a singlet. So besides the standard model of Lagrangian, then this is the Lagrangian. If you insist your theory is a renormative distribution theory, then this is the sort of thing. By the way, this has lambda D here is the self-interaction in the parameter, which if all these problems in the previous Feynman's talk exist, so self-interaction may smooth or soften the problem. So, but then for direct detection and also the relic density, this does not play much a role. Okay, so after, of course, then in order for the document to be stable, then this you have a Z2 symmetry, and this Z2 symmetry is not broken such that this D is stable, and then play the role of document. And of course, then this edge is the Higgs doublet, but then this has to have what is that? Vacuum exclusion value. So after you have the symmetry breaking, this is the vacuum exclusion value here, and then this becomes here. Then the mass of the dark matter is modified by this here, and then you have Higgs scatter dark matter annihilating to Higgs, or two Higgs dark matter, two dark matter annihilating the standard model of Higgs, and then the standard model of Higgs can propagate and become the standard model of particles. So, okay. So once you have this, Then you have all this, if you want to produce the relic density, then you just calculate all this. Depending on the mass, if it's larger than 2 heaps, then you also include this. If it's smaller, then you just appropriately take into account of given the final space. So once you get all